Let us see what are the contents in this subject, thermal engineering 1. The first chapter is fundamentals of thermodynamics, laws of perfect gases, thermodynamic processes in gases, fuels and combustion, air standard cycles, properties of steam, vapor power cycles. Now, I am going to take the first chapter, fundamental of thermodynamics. So, what do you mean by thermodynamics? Let us understand very clearly. Thermodynamics is the science which deals with heat and work and those properties of the substance which are connected with heat and work. Thermo means heat and dynamics means power. Here thermo is heat, heat is nothing but a form of energy, dynamics is nothing but force associated with the motion. So, both put together forms a thermodynamics. It is the branch of study of energy which treats heat in motion, such as conversion of heat energy into other forms. Mainly thermodynamics deals with transfer of heat from one medium to another. Here medium is most important, thermodynamic medium has to be used to convert energy into useful mechanical work. I will show you how heat energy is converted into mechanical work. Let me take example of cracker. It is a simple sketch of a cracker. It is filled with a fuel. Take a matchstick and ignite it, and after ignition you put a box over it. When it is ignited and expand, the force will be produced here and causing the box to get displaced. When it get displaced, work is said to be done. That means that heat is a form of energy. Energy is capacity to do the work. So, in thermodynamics we are learning how to convert heat into mechanical work. Let us see some of the applications of thermodynamics. Some of the applications are steam boilers, turbines, nuclear power plants, combustion systems, diesel and petrol engines, turbojets, rockets, gas turbines, air compressors, heat pumps, air conditioning systems, steam condensers and cooling towers, etc. These are the different applications based on the thermodynamics. So, now let us understand what is thermodynamic system. It is a system, it will have input, it has got output. Here input is heat, output is work. So, now here let us understand what you mean by thermodynamic system. System is a prescribed region in space or a finite quantity of matter upon which attention is focused for a study. System can be defined as it is a place where some thermodynamic activity will be happening. System is a region in space containing a certain quantity of matter, that is nothing but working fluid, whose behavior is studied, and everything external to the system is known as surroundings. Everything external to the system is called as what? Surroundings. An envelope enclosing the system is called boundary. This is the envelope which is enclosing the system, that we call it as a boundary. Boundary separate the system from the surroundings. The system and surroundings put together form a universe. System and surrounding put together forms a universe. The boundary may be real or imaginary. Moreover, it may be fixed or moving. Sometimes the boundary can be fixed, sometimes the boundary can be movable. Example, take an example of air balloon. As you fill up the air into the balloon, the boundary start moving. Next, let us understand classification of systems. There are three types of thermodynamic systems generally considered. First one is closed system, second one is open system, third one is isolated system. We will learn in detail one by one. First, let us understand what you mean by closed system. If the boundary of the system does not allow the matter is nothing but a mass, to cross over it, then it is known as closed system. Here the system contains fixed or movable across the boundary. Heat and work are the only ways in which energy can be transferred between closed system and its surroundings. As I told you while explaining the system will be covered with a boundary, and the transaction of the heat has to happen between the boundary. During that process, there will not be movement of the mass. A closed system thus is fully defined when the fluid inside is known. We should know what is the kind of fluid we are using it inside the vessel. Then how much mass of the fluid we have taken inside that, and the boundary between the fluid and the surroundings is defined. So, these are the characteristics on which the closed system works. Let me take example to make you to understand very clearly the closed system. I will explain about the hot water bag. So, all of us we are very familiar with hot water bag. It is used to warm the body. Okay. So, in this the system is hot water. You have to fill the hot water bag with hot water and close the cap and place it over the body. And when it is placed over the body, the heat will be only transferred, the mass will remain within the system. Let me take another example, IC engine. You can see here the system here is gas. It is completely enclosed in a piston and cylinder arrangement. The weights are added on the piston to control the movement of the piston. So, now the cylinder acts as a system boundary, and entire thing outside the system is called as surroundings. When the gas is either heated or cooled, it undergoes some process. As a result of that, so either heat is transferred or work is transferred on the system, but the mass of the system will be remain within the system, it will not go. Next, let us understand what you mean by open system. If the boundary of the system allows the matter to flow in to or out of the system, then it is known as open system. In open system, matter, that is nothing but a mass, crosses the boundary of the system. Here in this, heat and work may also cross the boundary. So, in this, when you see the in closed system, there is only energy transfer. In case of open system, both mass transfer as well as energy transfer is crossing the boundary. Let us understand with the example very clearly. I have taken the example of water geyser and also air compressor. Let me explain about the geyser. Here the electrical energy is supplied through the electrical coil. The heat is transferred from the surroundings to system. The cold water enters and the heat is absorbed, it absorbs the heat and goes out as a hot water. Here mass transfer is happening between the system and surroundings, and as well as the heat transfer is occurring. Similarly, another example, air compressor. As we know, air compressor is a device which is used to compress the air. Here the air compressor is connected with the help of the motor and shaft. Shaft supplies the mechanical energy to the system, and this causes the air compressor to suck the air inside and pressurizes it and delivers it at higher pressure. Here the air enters and enters from the surroundings to system, then system to surroundings. There is a mass transfer is happening, as well as the work transfer is also happening here. So, it is a system in which both energy transfer as well as mass transfer occurring. So, this is what we call it as a open system. Let us understand next isolated system. If the boundary of the system does not allow the matter, that is mass or the energy, to flow into or out of the system, then it is known as isolated system. It is completely isolated from the surroundings. There will not be any movement of the heat or mass between, there will not be any transaction between the system and surroundings. An isolated system is the one which is completely uninfluenced by the surroundings. It is of fixed mass and no heat or work crosses the boundary of the system. It is completely isolated. The example is thermodynamic universe, thermos flask, hot box, etc. can be considered as a isolated system. Next, let us understand, because if you want to understand the properties of the thermodynamic fluid, it is necessary for us to know the terminology which are used in thermodynamics. First one, the basic thing is PV diagram, that is most important. What do you mean by PV diagram? It is a diagram which is plotted with pressure on the y axis versus volume on the x axis. The area under PV diagram indicates the work done. The work done in the thermodynamic is the product of pressure and volume. In engineering mechanics, work done is equal to force into distance. But what do you mean by force? Force is equal to pressure by area. No, pressure is equal to force by area. Force is equal to pressure into area. If you substitute here, so then area into displacement will give you volume. Therefore, in thermodynamics, work done is product of pressure and volume. You can see here a graph. The pressure is plotted on the y axis, volume is plotted on the x axis. The area under PV diagram gives you work done, work required by the system. Next, we will understand about the state. You can see the PV diagram over here. The point number 1 indicates the state point 1. The point 2 indicates the state point 2. A state of a system is the condition and is identified through certain observable properties such as pressure, volume, temperature, density. Normally, 2 independent thermodynamic properties are sufficient to define the state in a closed system. You can see here on the PV diagram, the state point 1 indicates pressure P 1 and the volume V 1. When the system changes its state from 1 to 2, the pressure drops to P 2 and volume increases to V 2. You can see here 2 properties are required to define the particular state condition of the system. Next, path. Path is also called as change of state. It is a series of the states through which the system passes. It is the locus of successive states the system undergoes. Here, the system changes its state from 1 to 2. So, now it is passing through the series of state the system passes. So, now this is called as what? Path. Next, process. A system is said to have undergone a process when heat and work crosses its boundary. Heat enters into the system and work crosses the boundary. When the heat and work transaction is occurring, then it is called as what? Process. In such case, various properties of the system will change. When the state of a substance is changed by means of an operation carried out on that substance, then the substance is said to have undergone a process. In this case, you can see here there is a change of state, there is a change of state. Okay. So, here because of this there is a change of state occurring on the substance. So, when the change of state is occurring on the substance, it must have undergone the process. Some of the examples are expansion or compression of a gas, expansion of steam through a nozzle, conversion of water into steam, either heating or cooling. These are the different processes, generally we use it in thermodynamic processes. Next, cycle. When a system is in a given state, undergoes a number of different processes and finally returns to its initial state, then system is said to have undergone a cycle. Any process whose end states are identical is called as what? Cyclic process. I will draw a PV diagram here. The system is at this particular point 1. Now, its change of state is occurring through a path A and change of state is 2 now. Now, it comes back to state 1 through path B. This is, we call it as a cyclic process. Now, at the end of the process, initial conditions are restored and initial conditions are identical. Any process whose end states are identical is called as what? Cyclic process. The figure which I have shown here shows cyclic process. 1 A 2 B 1 is a cyclic process. Next, let us understand thermodynamic equilibrium. So, first let us understand what you mean by equilibrium. Equilibrium condition means there is no unbalanced forces, it is completely balanced. The net resultant is 0. Let us understand thermodynamic equilibrium. A system is said to be in thermal equilibrium when the temperature at all the points in the system is same. The temperature at all the points inside the system has to be same and identical. Thermal equilibrium denotes only in uniformity in temperature, So, now you take hot body, consider another body which is cold. This is about 60 degree centigrade and this is about 20 degree centigrade. Bring together, the heat start flowing from hot body to cold body till how long? The temperature of both become 40 degree centigrade. So, once these two becomes 40 degree centigrade, like 60 plus 20, 80 by 2, 40, the equilibrium condition is achieved. So, this is what we call it as a thermal equilibrium. Next, mechanical equilibrium. In mechanical equilibrium denotes only uniformity of pressure. There is no unbalanced pressure inside the system. In entire system, the pressure will be uniform and identical. Similarly, chemical equilibrium, which denotes absence of chemical reaction. So, two chemicals when initially added, they undergo reaction. So, they undergo reaction till they get neutralized. After neutralization, then there will not be any chemical reaction. That condition we call it as a chemical equilibrium. A system in a thermodynamic equilibrium is in complete equilibrium, that is, a system is in thermodynamic equilibrium if it is in mechanical, thermal and chemical equilibrium. If any system is said to be thermodynamic equilibrium, it must satisfy the condition like it should be thermal equilibrium, it should be mechanical equilibrium, it should be chemical equilibrium. The entire system is said to be thermodynamic equilibrium. Next, let us understand quasi-static process. The process during which the system remains almost in a state of thermodynamic equilibrium from one end state to other end state is called as quasi-static process. That means that during the change of state, the system will be remain in the equilibrium state. There will not be unequilibrium condition, never exist in that. That process we call it as a quasi-static process. A system exists in a state of a thermodynamic equilibrium when no change in any macroscopic property is registered if the system is isolated from the surroundings. Let us see how quasi-static process is occurring here. Consider the system is shown in the figure. If all the weights are removed suddenly, let me take example of this. This is a stopper and this is a piston. This is a thermodynamic system, fluid, gas. When any process is occurred on the gas which results in movement of the piston, the movement of the piston is not controlled. So, you will not get the equilibrium points over here. We do not have any control over the motion of the piston here. The movement of the piston is erratic, ununiform. So, now suppose if you want to make it uniform, you have the movement of the piston has to be controlled by adding the weights upon it. At every point, if you remove the weight, the specific distance the piston will travel. So, by doing so, we can achieve the equilibrium points when the system changes its state from 1 to 2 through the equilibrium points, then the process is said to be quasi-static process. Next, let us understand the definition of the property. A property of a system is an observable characteristic of a system. The quantities which define the state of a system are called as properties. Example, pressure, volume and temperature. Let me give one simple example on this. When we go to petrol bunk to fill our vehicles with the petrol, we will be watching only how much volume of the fluid going inside the petrol tank. So, instead of seeing the color of the petrol as well as the quality of the petrol. So, we are seeing the thermodynamic property in a macroscopic level. So, we are concentrating about pressure, volume and temperature. So, that is what it is called as an easily observable characteristic of the system. Let us understand how the properties have been classified. So, we have to know how the properties has been classified. Thermodynamic properties are generally divided into two categories, two classes. One is intensive property, it is also called it as qualitative properties. I will just define it, the properties which are independent of mass of the substance. That means that the value of the property does not depend upon the mass, it will not considered with the mass, then it is called as what? Intensive property. Example, pressure, temperature, density, specific gravity, specific volume, surface tension, thermal conductivity. I will give the one example, the pressure. So, I will take the example of human beings. The normal pressure, blood pressure has to be 120 by 80. If the fat man weighs more, slim man weighs less, but when the healthy condition is considered, the pressure of the both the bodies has to be same 120 by 80. So, here mass, the pressure is not depend upon the mass. Extensive or extrinsic or quantitative property. The property, the value of the property which are dependent on the size of the system and mass of the substance. Here mass is considered to define the particular property, then that property is called as what? Extensive property. Example, mass of the system, volume, weight, enthalpy, entropy, internal energy, these are considered with respect to the mass. Some quantities which are considered with respect to the mass, they are called as what? Extensive property, whose value depend upon the mass. A thermodynamic property, the characteristics of the thermodynamic property can be understood by the following points. It is a measurable characteristic of the system. It is that whose value must be independent of the processes, and it is that which depends only on the initial and final states of the system. You can see here, it is a measurable characteristic, and it is the one whose value must be independent, it is not be dependent on the process, and it depends only on the initial conditions as well as final condition of the system. The property depends only on the state of the system and not upon the manner in which the state was reached. We are not bothered to know how the state has changed, but we are bothered to know only the state of the system. Thus, property is a point function, not a path function. So, now let us understand what is the terms generally considered in thermodynamics. First one, pressure. Pressure of a gas is the force exerted by it per unit area on the sides or walls of the container due to the continuous collision of gas molecules. I will explain it once again. Pressure is generally mathematically is defined as force per unit area. Here the thermodynamic system, that is nothing but thermodynamic fluid, exert force on the walls of the container or sides of the container due to the internal collision of the gas molecules. It may be the momentum change of molecules bombarding the boundary of a system in unit time. It is an intensive property of the system whose value does not depend upon the mass. So, now I am going to explain about the absolute pressure. If the gauge pressure is positive and above the atmospheric, the P absolute pressure can be defined as sum of atmospheric pressure plus gauge pressure. If the gauge pressure is negative, absolute pressure can be calculated by atmospheric pressure minus vacuum pressure. So, P ABS stands for absolute pressure, P VAC stands for vacuum pressure, P ATM stands for atmospheric pressure, Pg stands for gauge pressure. Next, volume. Volume is the space occupied by the substance. It is measured in meter cube. Volume per unit mass of a substance is called as what? Specific volume. Here you can see here per kg is considered, is depend upon the mass here. Okay. Mass per unit volume is called as specific mass or density. Specific volume is reciprocal of density. Here density is volume per unit mass, mass per unit volume, specific volume is volume per unit mass. Next, temperature. Temperature of a fluid is the measure of the velocity of its molecule. When the fluid is heated, as a result of addition of the heat, the velocity of the particle increases. The measure of the velocity of the molecules is termed as temperature. Thus, temperature is a measure of kinetic energy, as kinetic energy varies with velocity. As you add more and more heat, the kinetic energy of the molecules increases, and the measure of that we term it as a velocity. A change in temperature of a system accounts for change in velocity of molecule. Temperature is an arbitrary scale of measuring the degree of heat. It is a scale which is used to measure the degree of the heat. Thus, when a body is heated, the molecules are set into motion, or the molecules in motion obtain higher velocity, resulting in rise in temperature. temperature is measured in international Celsius centigrade scale, that is degree centigrade. When a fluid is cooled below 0 degree centigrade, say up to 273.16 degree centigrade, that is minus 273 degree centigrade, this is a state of perfect vacuum and 0 pressure. Minus 273 degree centigrade is called as what? Perfect vacuum, state of perfect vacuum and 0 pressure. This temperature is called as absolute 0. The temperature at any point and above absolute 0 is called absolute temperature. Such a scale is called as what? Kelvin scale. Whenever if you want to measure the temperature above the absolute 0, then it is termed as Kelvin scale. Thus, degree Kelvin is equal to degree centigrade plus 273. Next, let us understand work. In a system, a force at the boundary of the system is moved through a distance. As I already had told you, work done is equal to force into displacement. In a system, a force at the boundary of the system is moved through a distance. Now, this is a thermodynamic system. Because of expansion, force is produced here and causing the piston to move to a certain distance x. So, force at the boundary of the system, this is the boundary, right. This is the boundary. So, when the force at the boundary of the system is moved through a distance, the work is said to be done by R on the system. As soon as the force ceases to be moved, then work also ceases. When the force becomes 0 and work becomes 0, work is therefore a transient quantity. In other words, work being the product of force and displacement, it is not stored in a system. It represents a form of energy that must be crossing the boundary. That boundary can be either real or imaginary of the system and can be called energy in transition. Being a transient quantity, work is not a property. Unit of work is generally in SI units is Newton meter or joule. So, 1 Newton meter is equal to 1 joule. Next, let us understand the power. The rate at which work is done by or upon the system is known as power. Unit of power in SI units is joules per second or watt. Let us know what is the definition of heat. Heat is defined as form of energy, that is thermal energy, that is transferred by virtue of temperature difference or temperature gradient. Here the potential difference to transfer the heat is temperature difference. If there is a temperature difference, then only the heat can transfer from one place to another place. Heat is a transient phenomenon because heat cannot be stored, but capable of moving from one place to another. Here heat is a path function, whereas work is a point function. Let us compare both heat and work here. There are many similarities between heat and thermodynamic work. Heat and work are not properties of the system. They exist only during interaction between the system and the boundary. They appear when change of state occurs and disappear when the process is completed. When the process starts, there will be interaction between the interaction of heat and work. When the process is completed, so both get nullified. Thus, heat and work both are transient phenomenon. Both heat and work are boundary phenomena, They are observed at the boundaries of the system and represent energy crossing the boundary. Here heat and work can be observed while crossing the boundary. Both heat and work are path functions. Heat is transferred because of temperature difference between the system and surroundings. Work is transferred, that is, work is the energy transfer associated with the force acting through a distance. So, next let us learn about the sign convention, and this is a system. The system absorbs the heat from the surroundings. When the heat enters from the surroundings to system, it is termed as positive heat. Heat flows to a system. When the system rejects the heat, when the heat flows from the system to the surroundings, it is termed as negative. It is denoted by negative Q. When the system produces the work after absorbing the heat, it is going to produce the work. This is what we call as a positive work. When the work is done on the system, it is termed as negative work. And if there is no heat transfer, Q is equal to 0. If there is no work transfer, then work is termed as what? 0. I will give an example. IC engine, internal combustion engine, it receives the heat and produces the work. Work is produced by the system and heat is absorbed from the surroundings to system. Both are denoted as positive work and positive heat. Air compressor, work is flowing from surroundings to system, negative work. Heat is going out of the system, negative heat. So, this is the way sign conventions can be understood. Next, internal energy. The internal energy of a perfect gas therefore consists of only the kinetic energy of its molecule. Kinetic energy increases with the rise of temperature. Thus, internal energy of the function, internal energy is the function of temperature. It rises or falls with the rise or fall of temperature. Internal energy, that is a point function and hence a property of the system. Internal energy is also called intrinsic or microscopic or molecular internal energy, since it is stored in the molecular and atomic structure of the system. Internal energy is expressed in joules or kilojoules, and energy per unit mass is termed as U is equal to internal energy per unit mass, joules per kg or kilojoules per kg is called as specific internal energy. When the internal energy considered with respect to the mass, then it is called as what? Specific internal energy. Next, specific heat. The specific heat of a substance is defined as amount of heat that enters or leaves a unit mass of the substance when it experiences 1 degree centigrade change in temperature. When the body temperature increases by 1 degree centigrade, how much amount of the heat required, that we call it as a specific heat. Specific heat is generally defined as the amount of heat supplied to a system to rise its temperature by 1 degree centigrade. Specific heat is a function of temperature. For solids and liquids, value of specific heat varies with the temperature and does not differ much for different processes. In case of gases, it depends on path of the process also. If heat is supplied to 1 kg gas keeping pressure constant through 1 degree temperature difference, then it is called as specific heat at constant pressure. When the pressure is kept constant during the rise of temperature by 1 degree centigrade, it is termed as specific heat at constant pressure. When heat is supplied to 1 kg gas keeping the volume constant through 1 degree temperature difference, it is called as specific heat as constant constant volume Cv. Cp and Cv are properties of the gas and are really not constant, but vary with pressure and temperature. They may, however, be assumed constant for moderate changes of pressure and temperature. Energy. Energy is defined as capacity to do the work. In more general form, it can be defined as the capacity to exert a force through a distance. Energy cannot be seen or cannot have any substance. Presence of energy is indicated by the properties of matter, such as the pressure, density, etc. If energy is added or removed from a substance, there will be a change in one or more properties of the substance. Energy appears in many forms, that is mechanical, potential energy and kinetic energy, internal energy, electrical energy, chemical energy, nuclear energy, work, heat energy, etc. Energy can be classified into two types. One is stored energy, another one is transit energy. The energy can be stored in a body is called as stored energy, that is kinetic energy and potential energy. The energy cannot be stored, it is always try to move from one place to another place, it is called as transit energy. Heat energy is the example for transit energy. Next, let us understand the STP. STP means standard temperature and pressure. Pressure is taken as equivalent to 760 millimeter of mercury column and temperature is 15 degrees centigrade. 760 millimeters of mercury is equal to 1.01325 bar, that is atmospheric pressure. Next, NTP, normal temperature and pressure. Temperature is taken as 0 degree centigrade, pressure is taken as 1 atmospheric pressure, that is 1.01325 bar. Volume occupied by a gas at NTP is known as normal volume. Vacuum. If in a system there is no pressure, then it is said to be in a perfect vacuum. If the pressure of the system is less than the atmospheric, then it is said to be impartial vacuum, or it is also called as negative gauge pressure. Next, the another definition is enthalpy. Enthalpy is defined as the heat supplied to a system at constant pressure. It is a property of a system and thus it is a point function. It is indicated by H is equal to m into Cp into dt, where H is enthalpy, m is mass of the gas, dt is temperature difference, Cp is specific heat at constant pressure. Next, the definition of entropy. It is a thermodynamic property of working substance which is a function of heat added. It increases with addition of heat and decreases with removal of heat. The small increase of entropy of a substance is the ratio of a small addition of heat to the absolute temperature. It is indicated by the formula ds is equal to dq by T, where ds is change in entropy, dq is addition of heat, T is the absolute temperature. Entropy cannot be measured by any instrument as it, and it is not the physical property of the substance. As the property entropy depends on the mass of the system, it is an extensive property. Absolute value of entropy cannot be determined, but the change in its value can be determined. The unit of entropy is kilojoules per kg Kelvin. This is the unit is considered. Next, understand laws of thermodynamics. There are three laws of thermodynamics. They are zeroth law of thermodynamics, first law of thermodynamics, second law of thermodynamics. First one, let us understand zeroth law of thermodynamics. You can consider here three bodies, body A, body B and body C. Now, here body A is thermal equilibrium with body C, body B is thermal equilibrium with body C, then that means that A and B must be thermally equilibrium with each other. This is the definition of Zeroth law. This law states that if two systems are in thermal equilibrium with third system, then they are also in thermal equilibrium with each other. If the bodies A and B are in thermal equilibrium with body C, then A and B must be thermally equilibrium with each other. When two systems are in thermal equilibrium, then the temperature, which is one of the properties of a system, will be same in case of two systems. Thus, it can be concluded that the temperature is that character or property of a system which determines whether or not the system is in thermal equilibrium. Next, let us understand first law of thermodynamics. First law of thermodynamics is nothing but law of conservation of energy. In this, energy neither be created nor destroyed, but transferred from one form to another. Energy, however, can be converted from one form to another form. The first law can be stated as the heat and work are mutually convertible. First law of the thermodynamics may be expressed as follows. If a system is operated through a closed cycle, the net heat transfer is directly proportional to the net work transfer. Mathematically, it may be expressed with cyclic integral as cyclic integral of heat, cyclic integral of work done. Here, cyclic integral of heat is nothing but net heat transfer, cyclic integral of work done is net work transfer. According to this law, the heat energy supplied to the system is equal to the sum of gain in internal energy and external work done. Therefore, heat transferred is equal to change in energy and sum of change in energy and work done. So, change in energy is nothing but E 2 minus E 1. E 1 is initial internal energy, E 2 is final internal energy, E 2 minus E 1 is the net change in internal energy. So, du stands for change in internal energy, W stands for external work done on the system, Q is the total heat supplied during the process. What are the limitations of first law of thermodynamics? When a closed system undergoes a thermodynamic cycle, the net heat transfer is equal to the net work transfer. This statement does not specify the direction of flow of heat and work, whether the heat flow from a hot body to a cold body or from a cold body to a hot body. It also does not give any condition under which this transfer takes place. The heat energy and mechanical work are mutually convertible. Though the mechanical work can be fully converted into heat energy, but only a part of heat energy can be converted into mechanical work. This means that the heat energy and mechanical work are not fully mutually convertible. In other words, this is a limitation on the conservation of one form of energy into another. These are the two limitations of thermodynamics. Next, second law of thermodynamics. So, in second law of thermodynamics, there are two statements. One is Kelvin-Planck statement, that I am going to explain it now. It is impossible for a self-acting machine working in a cyclic process whose sole purpose is to convert heat energy into mechanical work. There is a degradation of energy in the process of producing mechanical work from heat. You can see here, this is a source, high temperature reservoir, this is the heat engine which converts heat energy into mechanical work. From the source, the engine is receiving Q amount of the heat and converting W amount of work. So, in ideal condition only W can become heat supplied, but in reality it is not possible. It is impossible to construct a device whose sole purpose is to convert all the heat into mechanical work. It can also be stated, it is impossible to construct a device which operating in a cycle will produce no effect except the rising of a weight and the cooling of a heat reservoir. Next, Clausius statement. This is another statement of second law of thermodynamics. This law states that heat cannot flow from cold body to hot body without the help of external agency. You can see here how can it is possible to remove the heat from the cold body and reject to the hot body. So, there should be a potential difference, or else we have to use some heat pump to pump the heat from the cold body to hot body. This law can be stated in various ways of the following. Heat cannot itself flow from a low temperature to high temperature. It is impossible to construct a device which operating in a cycle will produce no effect other than the transfer of the heat from a colder body to a hotter body. Next, steady flow energy equation. So, now we have to understand this is also abbreviated as SFEE, steady flow energy equation. So, what are the assumptions made while deriving this steady flow energy equation? Assumptions: rate of mass inflow is same as rate of mass outflow. That means that rate of mass inflow should be equal to the rate of mass outflow. That means the mass of the fluid remains constant within the system. No chemical energy change is involved, as there is no change in chemical composition of the system. That means that the chemical neutrality has to be maintained in this. Rates at which heat and work crosses the boundary are constant. So, m is mass of the system, z is the location or elevation. You can see here location of the inlet and location of the position of the inlet and outlet. V is the velocity at which the fluid is entering into this. U is the specific internal energy carried by the fluid. H is the specific enthalpy which is carried by the fluid. That is specific enthalpy, it is related to the per unit mass. Vs indicates specific volume, the volume per unit mass. So, P is the pressure, it is expressed in terms of Newton per meter square. Q is the amount of heat supplied to the system, and W is the amount of work produced by the system or delivered by the system. Then E is total energy of the total storage of energy. So, now here this is the position 1 and this is the position 2. 1 and 2 indicates the properties at inlet and outlet of the system. The steady flow energy equation is given by the equation m into g into z1 plus v1 square by 2 plus h1. This is enthalpy, this is kinetic energy, and this is the potential energy. This is kinetic energy, enthalpy. So, plus heat added to the system is equal to m into g z2 plus v2 square by 2 plus h2 plus work produced. So, this equation is called as what? Steady flow energy equation. So, this completes your first chapter.